Hi everyone, I'm Marco Rudolph, and here I introduce our work Same but DifferNet, Semi-Supervised Defect Detection with Normalizing Flows. Me and the co-authors Bastian Wandt and Bodo Rosenhahn are from the Institute for Information Processing at the Leibniz University of Hannover. Here we go. What do we do and why? We want to detect if a product is defective from an image, which is important to ensure product quality and safety standards. For example, here at the upper right, we see a defect in form of a cut isolation of a cable. Now, if you want to acquire data to train a model on this task, you will meet some problems. Many defects are rare, and in the beginning you may have no single defective example. And even if you would, there could come up new defects after time. Due to this lack of data, a binary classification is not helpful or applicable for defect detection. This is why you have to perform a one-class classification, also known as anomaly or novelty detection. Here you only have access to one of the classes in training, which is in our case the class of non-defective products. In testing, the classificator should decide whether a given sample is member of this class. Here comes our approach DifferNet. It estimates the probability density of non-defective samples by transforming them to a latent space with a defined density. Now the assumption is that a low likelihood is an indicator for a defect, or to be more general, an anomaly. What makes DifferNet special is that it includes a normalizing flow, which maps bijectively. In this way, areas with a high likelihood in the latent space should be exclusively reserved for common samples, whereas uncommon samples are forcibly mapped to the remaining unlikely areas. This is a fundamental difference to generative models like generative adversarial networks or variational autoencoders, where the mapping as injective and likelihoods cannot be utilized in most cases. This is an overview of our pipeline. An input image is randomly transformed, e.g. by rotation, and resized to 3 different scales. We use an ImageNet pre-trained model, here AlexNet, to extract features and concatenate the feature vectors of the 3 scales to get the vector y. The density estimation is performed on y by having a normalizing flow that learns to transform it such that samples are normally distributed in the latent space Z. The feature extraction itself is not further optimized during training. The goal in training is to find parameters of the normalizing flow such that the likelihoods of training samples are maximized. This can be achieved by applying the negative log likelihood loss, which uses the change of variable formula. For more details about this and the normalizing flow architecture, which is close to real NVP, we refer to the paper. To judge whether a sample is defective or not, we define a score which is based on the negative log likelihood of the latent vector Z. In our case of a Gaussian distribution, this is equivalent to just using the L2 norm of Z. To have a robust score, we average this negative log likelihoods of 64 transformed images. The final decision can be made by simple thresholding, where a high score indicates a defect. In practice, this threshold can be set according to a desired false positive rate. Let's take a look at the experimental results. We varied this mentioned threshold to calculate the area under the ROC curve for detecting defects from the MVTech AD dataset. As can be seen, we set new state-of-the-art results for almost every class. Surprisingly, even the training on 16 out of 100 samples per class outperforms competitors. In contrast to several other approaches, ours is not optimized for localizing the defect on the image. Nevertheless, it can localize areas where anomalous features occur. Our method allows for propagating the negative log likelihood back to the input image. In the shown example, the hole in the carpet is highlighted through this technique because this area appears to have a big influence on the loss. Here we can see other examples of defective products of the MVTech AD dataset and the corresponding defect localizations. Our approach is able to localize defects of different types, sizes, and shapes. That's the end of my presentation, and if you want to ask or discuss something, come to our session or just write me a mail. A link to our GitHub repository is at the bottom of the slides. Bye!